Hello and welcome to another CMG Tech Byte video. My name is Marco Misenta and I'm a CMG simulation reservoir engineer. Today's video is about geothermal modeling, and specifically it will be about closed-loop single-well geothermal modeling. Here is a sketch of the process. We have a vertical well which is completed in a hot formation. The idea is to inject cold water from the top of the well into the annulus of this well and reproduce the same water back to surface via the tubing of the same well without the water entering the formation. The idea here is to extract heat from the formation via conduction and exchange this heat at surface. So to model this process, we need essentially two things. We need a wellbore model that is able to represent different strings and in a fully coupled way with the reservoir grid, and we need, of course, a thermal reservoir simulator. So we are going to show how, with the 2022 release of CMG, we have a interface in Builder, CMG's pre-processor tool, to build this type of model to characterize the formation in terms of thermal gradient and to build a discretized wellbore model for the simulator stars, which is CMG's thermal simulator. The other option that will be activated by Builder for stars will be the wellbore model in stars, which is flexible wellbore. FlexWell allows a collection of several tubing strings to be bundled up in an annular space in a fully coupled solution for the well. In the reservoir, we solve for mass, energy, momentum, conservation equations, and for Darcy law. In the discretized well, we will solve for the same conservation equations and for the pipe flow equation, and everything is done in a fully coupled way. Additionally, the radial conductive heat transfer from the well into the reservoir is accounted for, with the heat transfer from the tubing to the annulus, and then the heat transfer from annulus to reservoir, with the heat transfer coefficient being a function of the the thermal parameters of the different tubing strings and annular space. I'm going to show this in a demo. So let's have a look at this demo now. This is a base stars model that we want to turn into a closed loop single well geothermal model. At the moment, there is no temperature nor pressure defined in the model. And we also want to see how we can change this well model from a single well standard stars well model into a single well flexible wellbore model, where we can differentiate between annulus and tubing and characterize injection into the annulus and production via the tubing of the same well. Also, in this model, there is no overburden, and the overburden formation may be needed in this type of modeling options because the heat exchange in the overburden can be, of course, of interest. Now let's have a quick look at the porosity and permeability of this reservoir. 20% porosity and a low permeability of 1 in -3, but like I said, no definition for now of temperature and pressure. Back to components section, we can see that the only component here is water. There are no other components in the model, and we don't need to add any other components really. So now we can navigate to an interface that's been built in order to be able to input all this missing data in one go using a graphical user interface. This interface will be under the Process Wizard option under Components. So let's go to Process Wizard and let's expand this drop-down list of previous processes that were added through the years in Builder. Along with these, now with the Builder 2022 release, we have the geothermal option as well. I'm going to pick this option and go to the next step. And here we have 3 sub-options to choose from. The first is the conventional reservoir model for geothermal. The second option will be the closed-loop geothermal single well. And the third option will be the closed-loop geothermal with a U-shaped well. So in this case, we are going to focus on the second option only. So starting from the top here, we can check the option to extend the grid to include the overburden grid. And this will be layered in 20 additional layers. This can be changed if needed. The elevation of the top of the grid will be the top of the new final grid. And I'm going to assume that the top will be sea level, so that means 0 elevation. For distributing pressure, we need to have a reference depth, and this will be the top of the original grid, for example, 1,000 meters. And then we need a value of pressure at the reference depth, for instance, 11,000 kPa. In Show Thermal Controls, I can check this option to bring up the values of thermal conductivity and heat capacity for the reservoir zone and for the overburden zone. These parameters are typical standard parameters for conductivity and heat capacity. They can be overwritten if needed. Now I can go to the bottom actually of this window where we can see a table of depth subsea meters versus temperature. This is the table that will define the distribution of temperature in the reservoir, and it is dependent on the geothermal gradient. You can use this table, or you can copy and paste from a table you may have from your data. For instance, here I've got a table for a geothermal gradient curve. I can copy this table from, for instance, Excel, enter the number of rows of my table, 8, and then paste the data into Builder. Now I'm going to expand this window a bit, and I'll go back here to this FlexWell row that I've skipped before. Here is the point where we indicate to Builder which wells have to be converted to discretized wellbore modeling option, so the FlexWell option. In this case, I only have one well, so I'm just going to select my existing well 1 well. And once I click OK, I've got additional data for the wells to be input. So first of all, here we have a check option on use annulus for injection and tubing for production, and I'm going to accept this default. Cold water injection rate is defaulted to 100. I could double that to, for instance, 200. I'm just going to skip the installation a minute. At the bottom here of this blue line area, we can input the geometric characteristics of the wells in terms of the well really in terms of diameter. So we have the tubing diameter, inner and outer, the casing, inner and outer diameter, and the hole diameter size. These are default data. Again, this can be overwritten, but we also have a drop-down list of predefined geometric values for the diameters. And I'm going to pick, for example, one of these tubing 3.5 inch and hole size 11 inches. For the insulation thickness, I'm going to assume 1 inch thickness. So the insulation string in FlexWell is assumed to be associated to the tubing, so it will be an insulation sleeve around the tubing. Now this is the set of data necessary for defining all the missing parameters that we were talking about before. Now we will have flexible well bore, we will have extra grid blocks at the top to represent the overburden, we have the thermal characteristics of the model, and we have a geothermal gradient to distribute temperature with. I'm going to click Finish. This will update the model in various sections. Let's have a quick look at the main changes that happen in the model. So we can see now that the grid has been extended indeed up to 0 depth for representing surface. We can see that the well has been extended as well. And we have actually now 2 wells. Well 1 has been split, let's say, into well 1 annulus and tubing. They sit in the same location in the grid, but one well is an injector and the other one is a producer. If we open up the well events window, we can see that the injected fluid is, of course, water at a temperature which is defaulted to 15 Celsius, and the constraints are 200 cubic meters a day, as we said, plus there is an additional constraint on maximum BHP. For the well 1 tubing, this is a producer constraint on a minimum BHP. On top of this, the 2 wells are now belonging to the same FlexWell, and I can see now there is a new node here, FlexWell. I can double click on it just to show quickly that the FlexWell will be organized in annulus and tubing. The annulus will be well 1 annulus. And here we have the properties, the thermal properties of the FlexWell, the heat capacity of the wall, and the cement heat capacity and heat conductivities as well, and the relative roughness. So here again we have typical data. You can input your own data characteristic of your materials. If we consider the tubing interface, we can see the same information, but on top of that, I'd like to also highlight here the insulation outer diameter. For the tubing, like I said before, we can include an insulation string. In this simple example that I'm showing, it is assumed that the insulation string extends from top to bottom of the well. But this is not necessary. If the insulation string was shorter, you could do that by go and manually change the insulation outer diameter to be the same as the wall outer diameter. So it will be 0.089 in as many blocks here as needed, and this will set the insulation thickness to 0. In this case, I'm not going to do that. I'm just going to assume that the insulation string extends all the way through the tubing, but that's not a mandatory option. Let's now cancel this. So I go back to the main view. I just want to have a quick look at pressure. You can see now the pressure is defined. And temperature, we have a temperature of about 18 at the top and 234, 240 at the bottom of the well. Now, this model is ready to be submitted to STARS, but before doing that, let's go to the I/O control section, input-output section, to add some specific output parameters for FlexWell that we can plot in results. So I'm just going to add a row here for FlexWell and maybe go for all variables and then click OK. And then we go and save this model as my closed loop 1 well without base. Okay. Before submitting the model to STARS, we will add some keywords that are necessary for initializing FlexWell. So I'm just going to get these keywords and also, as I've just done, opening the model in cEdit. I'm just going to go to the Western recurrent data, identify the flexible wellbore definition, which is here, and input these keywords here which specify the initial pressure, temperature, and composition of the fluid inside a flexible wellbore. I will save the model. This model runs from 2020 January 1st down to last date is 2021 January 1st. So it's just a 1 year recirculation of water, and the model is very small, so I can definitely run it here and it will be a very fast run time. We can see here the model has run, and you can see already from the log file that we have been injecting 200 cubic meters a day and producing as much. We can open the model in results and check that the two wells belonging to the same FlexWell are indeed injecting and producing the same rate. As we can see here, they are. This is the well annulus water rate and then tubing water rate, and they're both at 200 cubic meters a day. Various things can be plotted and checked in the output now, but one thing I want to highlight is the possibility of plotting the produced and injected fluid temperature along the well by using the profile node in results and checking the data type here, FlexWell. I can start from the annulus and plot temperature along the annulus at a specific time step of the values available. Let's go for the last time step. This will be a plot of temperature versus distance. The top of the well will be here, of course, and we are injecting at about 16 Celsius as expected, and this is the temperature at the bottom of the annulus, which is our injector. I can maybe change the color to yellow, red, and then for our tubing, I can plot the same thing, and here we can compare the produced fluid temperature, 61 Celsius, which compares to 16 Celsius injection temperature, showing this increase in temperature. The gap between injected and produced temperature of the water that's been injected and produced is of course a function of various parameters related to for instance the thermal characteristics of the well, heat conduction and heat capacity, but also we have an insulation string there, and we have input a thickness for the insulation string. Maybe changing the thickness will also alter this result. So some sensitivity analysis on those parameters could be done starting from a base model like the one we have just built. Thank you very much for your attention.